once you, let's look at or talk about two random variables and their joined description. And once we understand two, it's easy to get on to 3, 4, etc. And and we already learned about one random variable, right? A random variable has its distribution function, which is the probability of the random variable taking values less than or equal to x. And that also, another way is using the density function, which is the derivative of the distribution function, etc. So we learned, and the density function had the density function can be used to describe the distribution function also by integration. So if you have the density function, then this area is the probability of x being greater than x1 and less than or equal to x2. So the whole area is 1. So this area is, of course, a fraction probability. That is in terms of, that's the meaning of the density function. So what if we are given two random variables? Of course, they are relevant to each other. That's the reason we talk about them. So we'll also bring in the notion of dependency and independence, etc. So think of a person's height and weight or income, whatever, right? So you can multiple random variables might be required to describe a phenomenon, and how do you describe all this these two together? So we can take the clue from here. So we can, instead of so in each case you have this is the distribution function of x as we have, and the same thing for y also. So this should give us this notion of trying to, so if I call this to be A and this to be B, then I can, to describe them together, the logical way seems to be to look at the events which satisfy both of these simultaneously together, and, right? We want this to happen and this to happen. So what is the probability of A intersection B? A and B. But A deals with the random variable x and B deals with the random variable y. So we bring it in together. Here it's not the same thing. We are looking at each one of them separately. Whether is there a difference between the two, we will see. So if this is the notation here, at least using the same notation, I am going to call it, it's a function of x and y. That's very clear. This is x, this is y. And we are dealing with the different random variables. So that I put it in the address box, x, y, x comma y. This is not multiplication or anything, just a notation. Saying that we are dealing with the random, this is saying that which values we are dealing with. So if this is x naught here, this will be x naught here. If this is y1 here, this will be y1. That's not going to change here. So question is, what is the properties of this function? So you can clearly see, whatever it is a probability. So this is a non-negative function. So fxy, x comma y is the probability of this set of all events that x of x is less than or equal to x, and y of psi is also less than. But we just write it as this fashion, x less than or equal. So we are talking about the probability of the events which satisfy both these inequalities simultaneously. So this is non-negative. And again, you can see what happens if you put any one of these variables to be minus infinity. Anyone? If you put x equal to minus infinity, this is minus infinity. X less than or equal to minus infinity is the null set. Null set intersection with anything is, so we get these relations, right? fxy minus infinity y, fxy x minus infinity, this is 0. What if you put both plus infinity? Anybody? Because this is whole set, so that's 1, so that's easy. So now let's put one of them to be plus infinity. And so I'm going to put, let's say, this is x plus infinity. So this is probability of x less than or equal to x intersection with y less than or equal to plus infinity. But this is the whole set. Any set intersection with the whole set is itself. So that's probability of x less than y. And we call that to be what? Distribution function of x. So the interesting thing is this function has the distribution function of x inside it. And similarly, if you put plus infinity here and comma y, this will turn out to be what? This will be a whole set. So that's just the probability of x less than or equal to plus infinity intersection y less than y. That's just a y less than y. So that's the distribution function of y. So you can see that this one definitely has both this information contained in it, but maybe more. And also I'm going to show that this function is monotonically non-decreasing. In other words, if x2 is greater than x1, I'm going to show that and it is true the other way also. You can write it if y2 is greater than y1. So let me show one of them. Right, this is we went through this argument before, right? And a variable less than equal to x2 is the disjoint union of x less than x1 and x living between x1 and x2. On the right side, the two sets are mutually exclusive. So now let me take the intersection with b here. I'm going to call b here. So that will be b here, b here. But b is y less than or equal to y. So what do you get? So let me put it together. So you get x less than or equal to x2, intersection with y less than y equals x less than x1, intersection with y less than y. This one, union x between x1 and x2, intersection with y less than y. So let's take I'll do the here. Let me do the probabilities here. This is the probability is going to be the sum of the probabilities because those two are mutually exclusive. So I get, here you can write one more line, probability of this plus probability of this. But look at this term. This is by definition here. Here, right? So that's by definition, this term is f of xy, x2 comma y equal to fxy, x1 comma y plus a probability of x greater than x1 less than x2 intersection y less than y. So what is my point? Look at here, this being a probability, this is non-negative. So you can see this number has to be greater than this because this number minus this number is non-negative. So this is true. Similarly, you can prove this to be true. So the function in either direction it is just monotonically non-decreasing. So we will call this, and final value is 1. So look at this function. It starts from 0, 0. And it never goes down. It goes in any direction. It is sort of it is non-decreasing, and at infinity, whether in the x direction or y direction, ultimately when both the variables go to, it goes to 1. So it has got all the properties of the distribution function. So we will call this a joint distribution function. This one. A joint PDF. We are dealing with the probability distribution function. So you saw the properties there. I'm just copying from this line. This minus this is that. And of course, fxy, x comma y is probability of x less than x intersection with y less than y. And this is the joined PDF. Probability distribution function or cumulative distribution function. Now, if you have a function, you can take its derivative. So we have two variables. So you can do this. So this is, we'll denote it by small f. That's also a function of x comma y. Again, going through the same delta x, delta y. This is non-negative. And going the other way, we can write capital Fxy, x naught comma y naught to be I'm just using it's the integral, right? The other way. So from here you get that. You can get the density function or the distribution. So what happens if you put plus infinity here? The value will be? So you get the property that why we call it so we'll call this the joined derivative function, or let me show you the so here dx dy is 1. So we can call it a density function because the total area in over 2 dimensions is 1. So it's a non-negative function. So we'll call this a joined PDF. So like the one random variable case, this is the complete description about 2 random variables using the joined distribution function or the density function. So as I said, we already saw that the distribution function has the density, one random variable distribution functions embedded in it. So how do we extract the density function of x and y from this? That's sort of the next goal. In other words, well, we'll see here. The answer is here, right? Look at here. So let's put these things together. To get the distribution function, this is the joint distribution function you can get from the joint density function. So look at this. Let's put let's do what we have done here. Let's put this y naught to be plus infinity. So I'll write it here. So fxy x comma y plus infinity is from the integral. So x naught. Let's say this is minus infinity to x naught, minus infinity to plus infinity fxy x comma y dx dy. And I'm going to change, instead of x naught, I want to call x here. So I'm going to change this x to, it's a running variable u. So that I can call this x. I don't have to, but this is good. But remember, from somewhere here, look at here. If you do this, there is, here. If you put the second variable to plus infinity, you get fx of x. So this is fx of x. How do you get small fx of x? Anyone from here? You derivative with respect to x. So from here, small fxx is d by dx of fx of x. And this is where you're going to see something new. So we need to take the derivative of the limits and so on, so it gets complicated. Or maybe there is something for you here. This should be dy du. This integral is with respect to y. This integral is with respect to the first variable. And similarly, the other one also, let me do both. So similarly, we should be able to write fyy is fxy plus infinity comma y. So fyy is the derivative of that, d by d of. So if you know how to do one, we can do the other one. So let me give you a formula to do it. This will turn out to be useful again and again. So that's the interesting thing is, of course, if this is constant, so we want to take the derivative of g with respect to x. If this is constant, it is easy, just the derivative of this with respect to x. So look at our case here. The limits have got the variable, right? So I think this is known as Leibniz rule. I have the derivation. I'll dig it out and give it to you. Or maybe there is a video, I don't know. But anyway, you can do it also. Just simple calculus, put gx plus delta x plus delta x, x plus delta x, x plus delta x. Bx plus delta x will be, so we have b of x plus delta x. How do you expand it? Bx plus Taylor series? What is it? You have to get through this course. Right, first derivative, etc. Right. So you multiply, same thing here, manipulate. I'm going to write down the results. So the result will turn out to be derivative of the top limit. Then wherever the variable is, you substitute the value. That's the way it will come out. You can derive this very easily. You can derive it. Minus the derivative of the bottom limit. Same thing. Substitute variable where the variable is the bottom limit. So the bottom limit and the top limit go there. And the third one is what you would do. Leave a and b as they are. Take the derivative with respect to please go home and derive this. You should be able to derive this. Just a simple exercise. As I said, I will give you the form for derivation also. And so let's substitute here. Look here. So derivative of the top limit, what is it? Derivative of x with respect to x, that what? 1. So that's your b prime. So this will have 3 terms. The top derivative of the top limit. Then what is the variable of variable? What is the variable here? Anybody? Variable here is right. So I need to rewrite this. This is with respect to u, isn't it? So wherever you see u, you substitute the top limit. Look at pay attention here, please. You have to look at this. The variable here is u, right? So wherever u appears here, you substitute the top limit. So that's going to be minus infinity to plus infinity fxy x comma. Instead of u, it will be x comma y minus, dy of course. Minus the derivative of the bottom limit. That will be 0. You need to practice this because this is going to hit you hard next week. So that's a 0, so there is no contribution. The third is the derivative of the inside quantity with respect to x. What's the derivative of this with respect to x? Look at that. There is no x there, so it is 0. So the answer is quite simple. So the answer turns out to be simply, we just take the density function, integrate out y. So I'll write down. And same thing here, if you take the derivative quickly here, this derivative goes here, so that's minus infinity to plus infinity. Derivative of the top limit, what's the variable here in this one? V. So y goes into V, so this is fxy x comma y, minus the derivative of the bottom limit 0, derivative of this with respect to y 0. So this is just the answer.